So I would say we just convinced ourselves, but really it was just me sort of saying words. So you don't have to be convinced of this. But one of the most important things that we would want to know about a linear transformation is it invertible? Is there another linear transformation that can exactly undo whatever my original transformation does? Can I go back and also forth in my linear transformation? So if I look at my cat pictures, right, every pixel on my original cat face over here in my domain is associated with exactly one pixel in the image of my transformed cat face over here. And so I can go both directions, right? The cat's left eye in the domain is associated with the image of the cat's left eye, which I guess I have to zoom out a little bit to see, in the codomain, right? Left eye corresponds to this left eye, and it's a one-to-one correspondence, right? We can go back and forth. Every point in the domain is associated with a unique point in the codomain because we have a function, but also every point in the codomain is associated with a unique point in the domain. That's the real magic of an invertible transformation. So whatever I did to transform this cat's face into this transformed face, there is another linear transformation that does the reverse and can get me back to start, right? And so the first thing that we need to figure out is what should it mean at the level of matrices for us to take one linear transformation and another linear transformation and chain them together to feed the output of one linear transformation into the input of another to form the composite function, right? The composite linear transformation. How does that show up at the level of matrices? And so this is where the algebra of matrices actually becomes algebra. So we've seen kind of how to add a matrix to another matrix, and that wasn't that interesting at the time. We can multiply matrices by scalars, and that's not particularly interesting either. A little bit, maybe. But what's really vibrant about matrices is that they do more than just form a vector space. They form an algebra. We can not only add matrices and multiply them by scalars, we can also multiply matrices by matrices. And it just so happens that multiplying a matrix by a matrix is the same thing as composing their linear transformations one with another. Right? So we replace function composition, which is a really hard algebraic operation. We replace it with multiplication of matrices, which is still hard, but it's not anywhere near as hard as thinking about what composite functions should look like in a general setting. So let's get an introduction to what matrix multiplication ought to be and what it ought to look like. So this is what I was just talking about, that the product of two matrices should be a matrix which represents the composition of the two linear transformations represented by those matrices. And so just to get ourselves started, we should figure out that that composition is even possible. So the first activity in this section just asks us to make the connection between the dimensions of a standard matrix and the dimensions of the domain and the codomain of the linear transformation represented by that matrix. So let's just take 5 minutes to do this first activity in 4.1, which in the textbook is 4.1.1, and in your activity sheets is otherwise known as 4.1. As it finally loads up here, 4.1.3. And actually, I've already done, no, I guess I haven't, 4.1.4. Sorry, so this is 4.1.4 in your activity sheet. So take a moment and figure out for the matrix A that has this standard matrix and for the transformation T that has this standard matrix, what should the domain and the codomain of the composite S composed with T be? So let's just take 5 minutes and have you do that discussion. We'll come back and come to some conclusions on that.
Hi. It seems like my group members left my breakout room.
Oh, bizarre. All right, I'll move you over into the other room here. Give that a try. All right, so what did you think about this question? So the question asks us to think about this composition. I'm going to switch my screen here in a second. So the standard matrix of T, because it transforms three-dimensional domain into a two-dimensional codomain, its standard matrix has 2 rows and 3 columns, right? Those columns are the images of the 3 standard basis vectors from R3 inside of R2. So remember, this is how we find the standard matrix of a linear transformation, is that we're just taking the 3 standard basis vectors. If I draw them in over here, red, yellow, and blue. Let's not use blue, let's say orange. So there are my 3 standard basis vectors in R3, and whatever their images are, so the first standard basis vector is going to 2, 5, wherever that is. The second standard basis vector is going to 1, -3, and so that's somewhere here in the 4th quadrant. And then the third standard basis vector is going to -3, 4, so that's somewhere here in the 2nd quadrant. All right, so that's what this first linear transformation is doing. It's taking these three standard basis vectors and transforming them into the three columns of the standard matrix of T. Then the standard matrix of S is doing the same thing with the two standard basis vectors of R2, which are otherwise known as 1, 0 and 0, 1. So if I draw those in here, then what the S transformation is doing is it's transforming those into two vectors in four-dimensional space. So wherever those two vectors happen to land over here, right? And so the question should be, what's happening to this entire transformation? It's going to take the three standard basis vectors of R3 and is going to place them inside of four-dimensional space. And so each of the columns of this standard matrix are going to be the image of one of these three standard basis vectors inside of four-dimensional space. So there's going to be three of them, three columns, right? E1, E2, and E3 of my original transformation. But then I'm going to be applying S of T of each of those things. S of T of E2, S of T of E3. And each of those is going to be a vector in four-dimensional space, and so it's going to have four components to it. And so ultimately, my composite matrix here that is going to be called the product matrix A times B, it's going to have as many columns as the domain of T did. So it's going to have as many columns as B. So it's going to have three columns. And it's going to have as many rows as the codomain of the A transformation. So it's going to have as many rows as the dimension of this codomain, which is the number of rows in the S matrix over here, which is 4. So the usual sort of rule of thumb for matching dimensions of matrices when we multiply them, A was 4 by 2, B was 2 by 3. And so we know that we can multiply them one by another because the number of columns in A matches the number of rows in B. And that's the dimension of this intermediate space here in the middle, which is the codomain for my first transformation, but it's also the domain for my second transformation in the chain. So as long as those numbers, as long as those dimensions match, we can actually do this multiplication. If they don't match, then we can't actually compose those two linear transformations, and so the matrix product makes no sense. But then it's the other two numbers that are telling me the number of rows and columns in the product matrix, 4 by 3, right? And that's where we get the dimensions of my product matrix.